Hello. So what I'd like to talk about today are some basically first year physics textbooks that I think are really good. In fact, first semester textbooks, just the Newtonian mechanics part. And I want to do this because I was watching a bunch of videos by people saying what sort of books they thought you should use for your first year of physics. And most of the people who were doing that basically went through the books that they used for their first year of physics. There was really one notable exception, whose name I don't remember, and I'm going to disagree with him, so I'm not going to actually name his name. But he was wonderful. He was a great curmudgeon, went through a bunch of books. He knew what he was talking about. But most of them were really just, this was the book I took physics from, right? And for their first year physics, for the first semester's worth of physics, these were the normal ones, right? Physics for Scientists and Engineers by Surway. There we go, Surway and Jewett. Then we have Holliday and Resnick, Fundamentals of Physics. These are all old ones. I'll tell you why in a moment. But those are the standard textbooks in physics. Those are probably the big ones. Uh, I'll probably show you another big one later on when I'm complaining about textbooks. The second edition, I think, of this is, I mean, this is the eighth, and that's a long time ago. Second edition of this, I think, is what I took um, physics with way back when, and the third edition was coming up. That was when editions lasted several years instead of half a semester. So most of the suggestions were really just people saying this was the textbook I used. Well, you didn't have a choice about that, and you possibly your professor had no choice in that. There's a good chance that everybody in the department came to a decision, or maybe just a committee in the department came to a decision for what people will use in the first year physics text. Um, so that's all right. The one guy that I liked when he pulled out one of these, and I think it was probably Holiday and Resnick, maybe it was Surway. No, it was Surway. He just said all of these are the same. They're not really the same, though, but he's about 90% right. Right? There's a contingent of well thought out, good, solid physics textbooks by people who really care about what they're teaching and really have thought about how to teach it. And one of these is this one, Six Ideas That Shaped Physics by Thomas A. More. And each book in this case is a thin book that talks about different aspects of physics. So that's actually going to be a good important thing. So you see here we have Unit C, conservation laws constrain interactions. That is the idea. That is the point of this book. You know, this booklet, this book, it's a book. I mean, even though this is small, it's still almost 300 pages. This book has a point, and it's conservation laws constrain interactions. This book, next to it, the laws of physics are universal. This book has a point. It tells you right on the cover it has a point. So already Thomas A. More, who is at a really nice school in California whose name I don't remember, it's a cluster of schools, and one of them's for science, one of them's for more liberal artsy stuff, and I forget which is which. And there might be even more. This guy has a point for each one of these 6 books, right? These are the old second edition. The third editions look like this. I was going to teach a E&M class over the summer if it went. This is what the third editions look like, so I had to pick up a third edition for E&M for that. So electric and magnetic fields are unified. I might talk a little bit more about that one in particular another time, just to talk about good introductory E&M textbooks for freshmen. So More has 6 of these. Unit C means conservation laws. Unit N means Newton's laws. E, we just saw there was for electricity and magnetism. R is for relativity, Q is for quantum mechanics, and T is for thermodynamics. So that would be 1.5 years, depending on where you are, how many credit hours, and so on, of physics you get, right? So I find these to be really well thought out, and I do that because he's done things a little bit differently, right? When you come to this book, it's not really thought out. It's a really good book, right? I love the problems in this book. There's some of these things. I think the best problems in these books are. Um, I don't even know if you're going to be able to see them or if I'm going to find one. There are two per chapter, and they're really awesome. Let's see. Can I find it? Oh, no. That's a what if. They're okay. Reviews are good. Oh, this is both of them. So the problems in this book actually are really good. You'll notice it has a review here. It has this color is it's sort of like the shape on a ski slope. Like the blue is intermediate on a ski slope, and green is um, easy, and the black is hard. Same thing here. Here only black is easy, blue is intermediate, and um, red way over here, that's hard. Very nice, nicely done. Halliday and Resnick does something similar. University Physics by Young and Friedman, or Young and Zemansky. No, Young and Friedman, yeah. Oh, it's Sears and Zemansky's University Physics by Young and Friedman. So this again, that's a very nice aspect. But right here, I love these problems. Why is the following situation impossible? That's a real good thinking problem for the students. And I also like these problems here that are review. And also this little S means they're symbolic, so they don't have any numbers. But the review, that means they definitely use something from an earlier chapter. Because all of these things build up on each other. And sometimes if you pick problems poorly, that's bad. So lots of good things about this book. Lots of good things about this book. I love some of the problems in here, especially the ones that deal with graphs. They have a really good set of problems dealing with data. But um, these books, these two books here, they don't have a point, right? They are just following the same formula that people have used over and over for years. And this was brought up in a 2009 AJ American Journal of Physics article or guest editorial by Craig Boren, Physics Textbook Writing Medieval Monastic Mimicry. He was really talking about the fact that if Survey decides to put something that's incorrect in his textbook, it'll show up in Halliday and Resnick, and it'll show up in Young and Friedman. It'll show up everywhere. Once there's an error in one of these textbooks, they just get written into all of those textbooks over and over and over again. But more to the point is these textbooks are the same, right? If you look at their chapter numbers, if you look at the order is almost exactly the same, and sometimes the chapter numbers are nearly the same. So, and I don't want to actually go in and look at those, but the idea here is that these two books are almost identical. Same thing with university physics. And they're almost identical because when you get your textbook committee, moving from Survey to Halliday and Resnick or back is almost effortless. You might have to choose a few new problems. You might have to, reorganize the syllabus marginally, but they're the same material in the same order with similar questions. Sometimes the questions are exactly the same. Sometimes they're marginally different, probably just to avoid lawsuits, but they're the same problem just with a tiny little difference in dressing. Not thought about. People didn't think too much about it. There are other ones like Modern Introductory Physics, which is an introductory physics class, not a modern physics class. Um, I don't like it as much, but it has a real point of view, which is that introductory physics should be building towards modern physics. We know where we're going with the introductory physics, and it's not just a stupid survey course. We're teaching physics, not giving you practice in a lot of little things that you're going to forget in 2 weeks anyway, which is what happens if you don't integrate the material. 6 ideas here. It had this really great reordering. So Moore says start with C. Right? Start with C and move to N. And so we're starting with conservation laws. We're starting with interactions here, right? First. Physics is about things interacting with each other. That's what the entire year is going to be about. Different things interacting with each other in different ways. Very interesting way to do it. And a very smart way to do it. Because when you start most of these things, when you come in here, the first 4 chapters, maybe 5 chapters, depending on this one, 4 chapters, almost all the same. Measurement, motion along a straight line, vectors, and motion in 2 and 3 dimensions are pseudophysics, right? They're more applied math, right? This is more applied math than physics. It's kinematics. Okay. Get into the physics in chapter 5, right? So depending on what you're doing, it's very easy to end up going a quarter of the semester, a third of the semester without actually getting to physics and just trying to go over the math without any of the physics content. Better to build the math with the physics content, in my view. And I think 6 Ideas does that admirably. So I really liked this situation. So another thing I really like about these guys is they are thin. All right. So when you look at a standard textbook like this one, let's see, where have we gotten? I've still got another chapter, particle physics and cosmology. Oh, is that the end? We're getting to the end sometime. I think that's the end. So 1522. 1522. 1,522 pages. This thing it takes up a quarter of your screen right now, I think. You can't carry this around. You need to be able to carry your physics textbook around so that you can actually read it and work problems and things like that. You need to go places. You can't just have a 50-pound textbook sitting here doing anything else. And when you look at these guys, you see they're about 300 pages. They're light. They're like little feathers. They're still full-size paper, right? So it's exactly full-size paper. It's exactly 8.5 by 11. So they're really good. They're really good size. I mean, if you're going to have paper around anyway, you may as well have something this size. It's not a big issue, but they're short, and they're something you can take around with you. And you're going to have to do the problems, and you're going to want to refer to the book if you're learning by yourself. So you're going to want something like this. Now, a lot of these books, like Sir Wayne Jewett, have a half-size book. This is a half-size book. This is Don't Panic. That's actually a fairly interesting. Don't Panic is actually a fairly interesting one as well. But this is just Volume 1 Mechanics. It has a Volume 2 for Electricity and Magnetism. It has a Volume 3, I think, for Modern Physics, although I don't think that exists. It's, an eighth of the size of your screen. It's still quite large, quite heavy. Although it says it's only 400 pages. I mean, the comparison, see, It's easy. So, I mean, this is probably because this has nicer paper rather than the regular textbook paper. And of course, you can get these in the same format. So these are also about the same size as this one. Right? These are broken up into probably 5 units, maybe 6, probably 5. Um, and they're very good. That's why I purchased these. I think I got the Halliday and Resnick um, like this because I'd seen it elsewhere. I'd seen somebody with one of them, or I actually, I went to different schools. So at a school after I'd taken my physics, I saw this was what they were selling. And they just sold like part one for physics one, or maybe they sold part one and part two. I'm not sure, but something like that. So that when you're carrying around your physics book, it's thin. So, you know, the guy who was complaining about these things all being the same, and he said, such and such is too thick. Well, these publishers agreed. So were they Addison Wesley and I think that's Addison Wesley. No, this is Wiley and this is Cengage. Uh, they agreed. I don't see the publisher for these guys. So they're good. So that's not really an excuse. You can break things down into reasonable chunks. Those books are good for a first semester. This is good for a first semester. So um, this is actually a little more. So I think it's really nice that they're thin. It's not the only thing. And so let's just flip through and see what it looks like on the inside since I've been talking for so long. I love this map, by the way. This is his map of physics. Really great. It's not the best categorization because it's just, lines on a graph. This is the history of physics, basically. This is a more conceptual thing, I think. Yeah, this is a more conceptual thing. Griffiths, for his introductory or for his junior level electrodynamics course, has an interesting square. And then, let's see, can I. In this book, Padmanabad has a nice one here, which says, okay, we've got 3 axes. Griffiths had 2 axes. Padmanabad has, I hope that's right, has more, has 3 axes instead of 2. That's good. Okay, so here we have 14 chapters, right? Um, Lots of little things in there. So he's going to start off with interactions. It's just the nature of science and things like that. Development and structure of physics. What's going to happen in this book. Um, different kinds of interactions and things like that. And skills, technical terms, and units. So they're just thrown out there. Then he has that introduction to vectors like those other guys. Vector operations and different things in 1 or 2 dimensions and so forth and so on. I should look at this because reference frames. I should look at this because one of the things that is important that I'm not sure, I can't tell from just this, and I didn't realize it was so important until 2 years ago, basically, is unit vectors. Students have a horrible time with unit vectors, and they need them to do the coursework. So that's there. Then we have interactions and transfer of momentum, illegal vector equations. Isn't that nice? We need more of that. But you have to talk about velocity and transfer of momentum, velocity and momentum, and then transferring momentum, what impulses and forces are. But here we're not dealing with forces too much, but we can talk a little bit about forces, mass and weight, momentum, flow, and motion. Particles and systems, so you have larger systems, applying momentum conservation. is that going to? Yeah, that's probably going to go into collisions. Let's see. Momentum conservation without isolation, degrees of isolation, problem-solving framework. No, very good. Constructing a model diagrams, solving conservation of momentum problems. Then we go into energy. So first, momentum, energy, potential energy functions, forces and energy, rotational energy, um, thermal energy, energy in bonds. So we're even getting into heat and things like that. Power, collisions, and impacts. Okay, so this is where we get to collisions. So that makes sense. So first we do conservation of momentum, then we do energy, and then we start talking about collisions. Then we have angular momentum, a little bit of that. Your cross product, very nice. Particle, rigid object, moving object, twirl, and torque. I have no idea what twirl is. I read this a long time ago, but I'm not sure. Precession of a top for conservation of angular momentum. Very good. So the three big conservation laws from the second half, usually from the second half of your first semester of physics, momentum, energy, and angular momentum, he does at the very beginning to emphasize the uh, the importance of the conservation law, because the conservation law is fundamental to physics, right? So Newton's laws are where they historically start, where physics historically really starts. I mean, most of these things have been in the air, actually, except for Newton's second law. I think probably you had 90% of the other two laws in there, maybe 100% of them possibly. But Newton's laws, when you put them all together, that's really where physics starts. No, that's where physics gets its start as a real analytical tool. Um, Galileo's experimental stuff may be a little bit more important in some other ways, but physics physics really gets its analytical bearings. The things that made people look at physics as something wondrous starts with Newton right then. But here are the suggested order. This is the suggested order: CNREQT from Thomas More. So if you had 3 semesters, probably it would end up CNETQR or something like that. There are reasons for having relativity and electromagnetism together, electricity and magnetism together. I'm not sure. I haven't seen enough of the relativity thing to be 100% sure about what Moore is doing, but he's probably does quite enough. He does bring up the relativity in the E&M book. And then in the second textbook here, those are look, I should have used that one. He has Newton's laws, and he starts with Newton's laws, vector calculus. Now this isn't this is sort of the beginnings of vector calculus. This is the time derivative of a vector, the definition of velocity, definition of acceleration, motion diagrams, um, things like that. So that's sort of the start of it. You haven't really gotten into div grad curl and all that stuff. Yeah, I mean that is a book, right? Probably ought to talk about that one too. It's hilarious. Um, so again, a little bit of physics, a little bit of math, and then more physics for the rest of the time. So physics from forces from motion. So you have description of motion. What are the forces? Motion from forces. You have a description of the forces. How do you get the motion? Statics. What happens if nothing goes? Linearly constrained motion. Stuff that has to go in a straight line. Coupled objects. Circularly constrained motion, things that go in a circle, non-inertial reference frames. So awesome, right? Uh, Here you're getting Galilean transformation, fictitious forces, um, inertial reference frames, all of those good things. So it's got its own chapter. I like that. In other places, these are topics that get swept to the back of a chapter, and maybe you get them, but probably you don't. Projectile motion, which we spend far too much time on in my experience at the very beginning of class before we've talked about physics. We start talking about projectiles. Here we have one chapter on it, which you have in normal textbooks, but it's right at the beginning, and this is what people start thinking physics is. And it's after we've done these other things with physics. So you see the drag forces here in chapter 6, and then we get drag and terminal speed in our projectile motion. So that's already here in your description of projectile motion. You don't have to sort of build it in with the kinematics ad hoc, which is what you'd have to do if you wanted to do anything with terminal speed at that point. Oscillatory motion, orbital motion, planetary motion. So a lot of good things at the end. So very good. This, again, a good set of books, nice and thin. They also have some good homework set. So homework is basic skills, synthetic problems, a little more challenging, and some rich context problems, but not a lot of each. So again, this is a book that is very nice because at the end of it you have 6, 12, 14, let's say 14 to 20 problems at each one. Whereas if I pull out this guy, if I pull this guy out, then oh, he has only 80 problems for waves. Probably other chapters earlier have more because waves are here. Only 95 in equilibrium and elasticity. Um, Dynamics and rotational motion still doesn't break 100. So if you want hundreds of problems, Young and Friedman, it's on the low end. It's on the low end. I know I can find better. Let's look over here. So let's see here. Did we break 167? Oh, I'm feeling so gypped. That does not, only 76. Man, I used to think these guys had hundreds. In fact, I know they had hundreds because I've assigned problems with over 100 as the number. So um, I might just go with this is an old textbook, so it's maybe it doesn't have as many as the current version. Oh, I'm so sad. So um, these guys have less than I thought. Although, again, the current textbook we're using definitely has over 100 because I just worked a bunch of problems for solutions to the homework that had over 100 as on it. But nice and small number of problems. An alternative text, which is a good one. This is an old one by AP French. This is a little kinder read, I think. I don't think it has anywhere near that number of problems. Right, so it still has 18. Some of them I think were large. I remember them. Yeah, so 31. Still a small number of problems. 29. This one's also quite good. So I think this is something that you could probably use if you were not quite as advanced a student in here. Again, it's an old book, but if this book has been in print since the 1960s, I think. No, yeah, 1965, with basically no changes in it, then probably there's a reason for that. This is a really good textbook as well. So this is an alternate that you might want to look at if you like the normal sort of way things get put together. But this is an excellent textbook back when They really cared about education instead of whatever we care about this week, which is, rather than making people understand, making them pass. Let's see, are there things in here? I mean, this is really good. Oh, I should show you some of the formula. So, oh, I don't want to show you those formulas, but I mean that those formula boxes are really nice. Um, oh, here's the overview for things. So here's the nice thing about these overview boxes, right? Is that he tells you the purpose, this defines all the symbols, says the limitations, where does this not work, and then he has some notes here. C is 0.5 for a sphere and typically less than 2. So different things about different stuff in there. And here is something to think about. I might have to start a podcast so I can get him online and ask him about why he used column vectors instead of other things, instead of the usual, which is in these textbooks for vectors. They usually use, if I can find some vectors, because they do weird things with them. They usually use this. They usually use the unit vector notation ijk usually instead of xyz. And those are left over from quaternions. They're not. There's no good reason to use ijk other than people have kept using them over and over in those physics textbooks for ages. But xyz would be better, I think. But he uses Moore uses these column vectors instead, and that seems completely reasonable to me. I think that probably does do some things visually that improve for the students what they're seeing. So I think that's probably a good thing, although it might have some effects later on when you have to try to start using unit vectors um, for other things. But this makes it very easy to see here, right, that minus mv squared over r is equal to 0 minus fl sine theta, and minus mg plus fl cosine theta is equal to 0, right, if you look at this equation here, which I don't know if you can see, but that's a really good visual way to do things, which might be better for some reasons than using the unit vectors. Unit vectors are really good for transformations. So again, very nice books. You can buy one at a time, so they're not quite as expensive. You can do just the ones you need. Probably they're more expensive. Let's see, can I see? I cannot see what the price is. The price is going to be pretty high. It's going to be $50, $75, $100 somewhere in there. Whereas these guys are upwards of $400 or $500 now. I don't know why I'm pretending this is heavy. It's only that much stuff. But anyways, so again, to reiterate, because I saw so many people doing things and so many people just going in through saying every physics textbook is the same, every first year physics textbook is the same. Well, no, it's not. These are different. This is different. I've got other ones that are different, but I left them at work. So this one's pretty close to the same, but it's still different. Very, very different ways of doing things, and I think we should probably acknowledge that there are those 10% of these physics textbooks that don't work, and they don't get picked up because there's a substantial number of physicists who were taught this way. They read that book, right, when they were 18, or for physicists maybe when they were 16 or 14, or their dad gave it to them for their birthday when they were 8 years old. I'm not sure. And they read this book. Everything was in this order, the same order it's been in since 1920. And they said, this has come down to me from God. This, can I move this so I can see all? This is the order for the topics in a physics class, and if you veer from that order for your topics in a physics class, you are wrong. You are wrong. Um, and that's the feedback I've gotten when I've talked to people about this. They'll just say things just like that, right? Um, oh, I don't like that. That's not the way I did it when I learned it. So, um, but I think this different sort of order of things, if done thoughtfully, I think Six Ideas does it thoughtfully. I think modern introductory physics does it thoughtfully. I think matter and interaction is a little bit different, but I don't remember it too much. And the copy I had was all loose leaf, so I'm not sure where it is. Um, but matter and interactions is an interesting one as well. But I still think Six Ideas is a little bit better. These are all very, very good books that I think you should look at instead of one of these if you're going to try to learn physics. Right? If you don't want to pay money, right? If you don't want to pay the money for Six Ideas, then and you just want to learn it on your own, then there's a open source textbook from Openstack's University Physics. It's a University Physics Volume 1, so it's one of these, about this size. It's actually a little bit longer since it's online and you can use it through HTML. Um, that that's a they don't really care so much about the page numbers, right? So if you're going to use one of these, if you're going to use Physics for Scientists and Engineers, if you're going to use Halliday, Resnick, and Walker, um, despite the fact that I like these better than the OpenStack textbook, you probably should just use the OpenStack textbook. It's good enough. It's from that same monastic medieval mimicry that these two guys are. But this guy, or these guys, written by Thomas A. More, they're not. They're individuals. Right? They have a point. Right? They have points, and that makes them much better textbooks, in my opinion, than these other textbooks. Okay, well, that is quite a soapbox, isn't it? How long have I talked? Almost 40 minutes. Okay, so um, if you want to learn first year physics, I think these are a good idea for you. Um, they're available, lots of places. So um, consider them. Thanks. Bye now.